I was just having a look before with Josh, but it's now up to 1.4 million views on YouTube, which just shows, there is actually quite a lot of interest in computer science beyond what sometimes it feels like. Yeah, and so what happened was, initially we were going to start producing the Raspberry Pis ourselves, and obviously when we got 100,000 pre-orders, the amount of capital we need to do that was a lot more than we had. We were bootstrapped. There's no VC money. There was kind of no. It was all our own financing, and so we partnered up with RS and Farnell and work on a licensing model where we license the design to them and they manufacture it and distribute. Initially, some of the manufacturing, initially all the manufacturing was done in China. Now all of the manufacturing, certainly of boards which are being sold outside China, is done in Wales in the UK. Which is very cool. It's cool that the cheapest computer you can buy is manufactured in Britain. You wouldn't really think about that. And we've moved that manufacturing from China to the UK. It's a pretty cool thing. And yeah, we sold about 1.5 million units of these now, all around the world. And that's a great thing. And as I say, it was designed with this aim of promoting computer science. We're very passionate about trying to get everyone to realise that programming, a bit of programming knowledge is valuable for just about any career these days. And equally we wanted to make sure that students, like there are many here, could afford to build those robots they always wanted to and still have enough money left over for beer. That was kind of our noble quest, right? And and I think we've come a long way to achieving that. So I would ordinarily at this point go through a lot of the technical specs, but I have a feeling most of the people in this audience will probably already know them. So what I think we'll do is I'll let Josh talk about his project, so we will cover some of the technical aspects as well, and then hopefully have lots of time for a Q&A afterwards. Great, so Josh.
All right. Well, I'll try to keep it short so we have lots of time for questions. I actually have a huge presentation here that but I'll just skip through a lot of this stuff just for the sake of time. So I'm a PhD candidate here at Boise State University, and I'm working in wireless sensor systems. And so I normally wouldn't have a whole lot of reason to use a Raspberry Pi because we're always designing, with microcontrollers in very small embedded systems. But when I started looking into developing some new communications protocols for wireless sensor networks, I came up with this idea that, well, it'd probably be easiest to test a lot of these ideas if I could just create a simulation that would allow me to do that, test all these ideas. And I thought, well, what's the best way I could do a simulation that would best emulate the wireless sensor nodes that I was working with. And I thought, well, what if you have a application running on each node in a cluster, and all of those communicate over Ethernet, but the scope of their communication is limited in the simulator to emulate that of a wireless sensor network. And so that's kind of how I got started in working in a cluster environment, but still on protocols for use in wireless sensor networks. And so on campus here we have a big Beowulf cluster that has 32 nodes. Many of you guys, if you've taken any computer science classes, you've probably been in the Onyx lab. How many people actually been in the Onyx lab? So most of you people over here. So it's just regular desktop computers. They're all hooked up on the same network, and you can actually issue parallel jobs against those computers. They'll all work on the same problem and return the results. That's basically what's going on. Go back through here. So, for anyone unfamiliar with what a Beowulf cluster is, really it's just a bunch of regular computers that are connected together through a common network, and they have some bits of software on there that allow them all to communicate with each other and share data and share processing. Virtually all of them use some kind of Linux-based operating system, and when you want to write programs that capitalize on all these processors, you need some way of doing that, and that's what this MPI language is. It's basically just a set of tools to write programs that allow you to do parallel computing. And so as an example, like I said, Onyx Lab has 32 nodes. They're all quad-core Intel processors, a whole bunch of RAM, and they're all running Fedora, which is a Linux distribution. And I kind of covered this. So the question is, so why would I want to, if I have Onyx cluster, why would I want to build my own cluster? And really this came down to, so 1 week during spring break this spring, Onyx was unavailable for me to use because they were doing some renovations in that room. So I got thinking, so I have this long-term project that I'm working on that requires a cluster. How can I ensure I always have a cluster available to me and one that I can customize in any way I want? And so as soon as I got thinking along those lines, I was like, well, what kind of hardware could I build a cluster of my own? How cheap could I do it? And we had recently been playing with Raspberry Pis a little bit in some of the work that we do in our lab as basically servers. So we'll connect our wireless sensor nodes to Raspberry Pis that upload data to central servers. So we had some lying around, and I go, well, let's see what we can do with that. So that's how this whole thing got started, was building a little cluster that could run my simulation and do so for as little cost as possible. And then there's a couple other things that you get with the Raspberry Pi that you wouldn't get in a normal desktop computer. And one is, you'll notice up here, these LEDs that are blinking on the side. Well, that's actually coming from a PCB, custom printed circuit board on there that we put our own LED on there. And its primary purpose is actually to allow the whole thing to be powered by regular computer power supplies. Normally a Raspberry Pi is powered by the little USB connector that's on the front. So all these are actually powered through that little board. And so aside from being able to toggle LEDs on and off, there's also these other hardware interfaces, the I2C and SPI. These are all common communications protocols used in embedded systems to talk to other kinds of chips. And that's useful for what we're trying to do. So the kind of idea of what was involved in creating this, basically you need 33 of a lot of parts. So we got 33 Raspberry Pis, and similarly, we got a whole bunch of SD cards, one for each board. Lots of Ethernet cables. This box on the bottom here is a big switch. So all those Ethernet cables run into that common switch. And again, we had to design that PCB that provides a way to distribute power to all the nodes that are there. So in terms of software on here, I'm running Arch Linux, which is a very lightweight version of Linux. It's kind of the bare bones distribution. So when you first install it on your computer or on your Raspberry Pi, you can connect to the internet and you have a basic command line interface, and that's it. There's no desktop environment or anything pre-installed. It supports all the other features that you can get in Raspbian, which is the most common Debian-based Linux. But the nice thing is that you're starting kind of on a clean slate. You just add only the things that you want. And the benefit of that is it only takes about 10 seconds. 10 seconds for one of these to boot up from a cold boot, so very quick. And how many of you guys know that you can overclock the Raspberry Pi to run at higher speeds? A few people, yeah. So all these are overclocked to run at 1 gigahertz rather than their normal 700 megahertz. And this is something that is supported by the Raspberry Pi organization. They're rated to do it, but they don't ship them that way. So, and as far as software required, basically just I wanted to be able to do parallel programming. I wanted to be able to have a shared file system with all of them, run Java, Python, and Perl. So this node up here is providing a network file system for all of the other ones. So the other ones, anytime the master writes something to its file system, the others can see what's there. And so these are just some of the packages that I installed on there to achieve the only things that are necessary to install to get a working cluster. And this kind of gives a graphical idea of how it's connected. So you have that switch, which all of those Pis are connected to, and then the master node, which is that one on the very top there, is providing the network file system for the rest. So pretty straightforward. And I'll skip over some of this stuff. So I talked about that little PCB board that's on the top there. And that's the circuit that there's. The center block there, that's just the header that has a bunch of pins on there. All I'm really doing is providing a way to get power into the board and drive a tricolor LED that's on the other side of it. So that's the Eagle CAD picture of it, and that's a very blurry picture of PCB up close. And then, so in the process of this, I was trying to figure out, well, how can you put all of these, you've got 33 of these things, how are you going to stack them in some orderly fashion? And so I came up with the idea of using PCB standoffs. So these are the type of things that normally would mount like the motherboard of your computer inside the case and hold it. That's what these basically are, just extra long versions. And so they're just threaded all together to build these stacks of 8. And then in order to keep all those stacks together, we decided to cut some plexiglass. So this is plexiglass on top here. Designed a little footprint in Eagle to lay out where they would be and drill the holes where they need to be. And so with that, I was going to show a couple little demos. The first one, this key blink one here, that one's already running right now, so you can kind of see what it is too. And effectively, so it's one program is written, which is started on this master node up here. And basically what happens is when you start the program here, the application gets spawned to all the nodes that are below it. And once they're all up and running, they can all share data and process them together. And all that's going on here is this node is sending commands to each of the ones below that are slaves to it to tell them when to turn their LED on and how long and what color they should do. And so anytime you see cases where multiple LEDs are turning on at the same time, the reason they can do that, since each of these are independent processors, right, but they're able to turn on at exactly the same time, that's because it's able to send a broadcast message over the Ethernet to tell it when to turn on. So that's the basic idea. So, so the last thing I'll just show, just to give you a little idea of how easy it is to do GPIO type things. So turn on an LED. I'll terminate that. Alright, so this is going to be fun because I didn't clear my monitor. Okay, so if I want to say turn on the LED on this board right here, I can do that with actually just some basic commands. So you can. So first off, I wrote a program. That do this. That just does one node. So you can So you can do a simple program that on any Raspberry Pi you can get it to control the LEDs on it. So that's a program written in C using a thing called Wiring Pi. So how many people have played with Arduinos at all? Okay, so a lot of you. So Wiring Pi is basically the same programming interface as Arduino, but for the Raspberry Pi. So you can change a digital I/O by saying, out, or whatever it is, output, or I can't remember now. digital write. Same idea. However, even if you don't want to do that, the Linux operating itself provides access to I/O pins like that. So let's see here. If I can go back here. So here's an example. So if you wanted to manually turn something on, you can there's these 3 commands. The first one here tells the operating system to allow you to work with a particular I/O pin that's on the device. The second one sets it as an output so that it can drive the pin one direction or another. And then the last one actually sets the value, so whether you want to turn it on or off. So as an example, I'll select this. It's interesting. I really should have mirrored these. I mirrored my display. This is terrible. So I'll send that one real quick. Sorry, my copy and paste didn't work too well here. Flash, GPIO, export. Okay. Well, I might need to skip this because this is kind of hard to do here with the. At any rate, the point is. You don't even have to know programming or anything to control pins and stuff on there. You can just directly access devices that are on the system. So, the last thing, just to kind of show how my application with my dissertation work running on there. So this is a video kind of showing. Probably do one more thing. Sorry. Go back here to that. Okay, so you get a little description of what's going on. So in my simulation, each node on the Raspberry Pi represents one node in the sensor network, and the distance that any node can communicate with any other node is controlled by the simulation. So this thing on the side here, just showing the radius that any one node can talk to another node. So for instance, if node 1 wants to talk to node 32, it can't do so directly. It has to send messages to all the nodes in between. And really, it can only talk to node 2 or 5 in this example. So what I did is I set up my simulation so that whenever one of these nodes sends a message, it lights one of its LEDs on the cluster, so you can actually see when a message is sent across in the simulation. You can see it move across on the device. So now I have a little video to do this because it is a little bit cumbersome to set up initially. So it goes through various stages. The first thing it has to do is establish a network, because since they can only talk to the node nearest them, it has to establish a network. So what you're seeing here is discovering where all the nodes are in the network, sending messages back and forth. And you see it kind of growing from the top down. That's node 1 started everything, and it's discovering where all the other nodes are in the network. So once it's established a network, then it starts sending messages to each node in the network. So in this example, you'll see packet. Node 1 at the top left is going to send a packet to every node in the rest of the system. So you see kind of it go down different paths as it makes its way to their target destination. So whenever the light's green, it's receiving or sending something. Whenever it's red, it's receiving something. And the last phase is a broadcast message. So node 1 sends a broadcast, and that propagates through the rest of the network. But this whole time, it's happening by hopping hopping through the network. All right. And lastly, so give an idea of what was all involved with building this. I kind of have a bill of materials that was involved in creating the whole thing, and basically for a little under $2,000, we were able to buy absolutely everything, put it together. Where you compare that to any traditional Beowulf cluster, you're going to spend at least hundreds of dollars for each node that you want to put together. So it's a pretty good price for the size of the cluster that you have. All right, so with that, take any questions.